Hey everyone, today we're going to talk about ruler and compass constructions. So if you think back to your geometry class, a compass is just a tool for creating circles. So on the left here, here's an image of a compass. And if you're not familiar with what a compass looks like, we're going to see an example of this very soon. And the ruler, well, everyone should be familiar with this. The ruler is used to make straight lines, right? You would take a pencil, align it with the edge of the ruler, and then from there you could create a straight line. So with these two tools, we can talk about how to construct a point. First, let's talk about the informal definition. So given these two tools, the compass and the ruler, there's three different combinations that we can put these two tools together, right? If we use if we use rulers, we can draw line segments, and whenever two line segments intersect, that creates a point, right? And if we move on to using one compass and one ruler, well, a compass will create a circle, a ruler will create a line, and the intersection of a circle and line segments also produces points. Lastly, if we use two compasses, well, we can have two circles, and if they intersect, they also intersect at a point. So on the right hand side here, we can see some examples of that, and the intersection points are in red here. These red points are what we call constructible points. Okay, so let's talk a little bit about the history of a constructible point, or not constructible points, but construction problems. Three of the classic ones are doubling the volume of a cube. So given a cube with some arbitrary volume, can we double the volume? Can we create a cube that actually has double the volume of the cube we're given? The second problem is, given some angle, are we able to break into three different angles, each of which are equivalent to each other? The last one is, given a circle of some area, can we create a square that has the same exact area? So the ancient Greeks knew how to solve these three problems with tools other than just ruler or compass. But if we restrict it down to just ruler and compass, the first time this problem was kind of talked about was also attributed to the ancient Greeks. And usually it's attributed to Plato or Euripides, and this is around 450 BCE. However, the ancient Greeks thought that just using the ruler and compass, these problems were just very, very hard to solve. They did not know it was impossible. And we can see that it wasn't until 1837 that Pierre showed that A and B are actually impossible to construct with just ruler and compass. So in the next part, we're going to look at some examples of how to use a compass and how to use a ruler to construct some points.
Hello everyone. So I'm going to be showing you what a compass is if you've never seen one. This is a slightly larger version of a compass than the ones you've probably seen. That's because this is for chalkboard drawing. But to give you a little taste of what it's like, it has kind of two legs that pull apart. And for this one, we have two pieces of chalk on either end, and there's this little bolt that can kind of screw it into place, so that if I wanted to draw a circle with radius of this length from each chalk to each chalk, I could easily put the compass on the board, kind of hold this one in place, and drag this one around in a circle. So this is my attempt at a circle. Oh gosh. Okay, it's very not perfect, but you know what? That's okay, because in life we all make mistakes. But you get the general idea. This is a circle with this very clear center, which has a radius of my choosing. Okay. And so using this beautiful contraption and just a straight edge, I'm going to show you how we can construct a perpendicular line through a point. So here, if you notice, we have a line, and there's a point on this line. How do we draw a perpendicular line through it? Well, I'm going to take my compass of whatever length I want, and I'm going to measure and draw a little portion of a circle right out there. I'm going to do the same thing on the other side. And because we've now, or notice there's this intersection, so I'm going to draw points at both of the intersections. And a quick thing to notice is that because these are both the same radii, right, it's the same length of the compass from here to here as it is from here to here, I'm just going to draw 2 lines there so that we know that those are congruent segments. Next thing I'm going to do is I'm going to unscrew this and make my circle a little bit larger. And I'm going to put one end on here, so this is the center of my circle. And I'm going to draw a little portion of a circle there, and I'm going to do the same thing over here. And because these lines intersect, I'm going to construct a point. And now we can actually connect these 2 points using the straight edge to form a perpendicular line. And if you're not convinced that this line is perpendicular, a quick explanation. That you can see that we have these 2 triangles right here. Well, we already said that this segment and this segment are congruent. You can also see that because this is the same radii as this radii, these 2 lines are also congruent. And this middle line is congruent to itself. And so because of the side triangle axiom, these 2 triangles must be congruent, which means that this angle is congruent to this angle, and because they're supplementary angles, that means they have to be right angles, and so these are perpendicular lines.
So now that we know how to construct a perpendicular bisector, we turn our attention to sort of what points and numbers we can actually construct, right? So say we have some line, and we choose some length, say this long, to be our unit length. And then we can take our compass, if we set it to this length, we can take it, and we can add successive marks to our line, and in so doing, essentially create a point that can correspond to each integer, right? So this is 0, 1, 2, and so on. And then, of course, you can go back this way for the negatives. But now that we have the integers, the question becomes, how can you get all of the rationals? Can you multiply? Can you divide these? And contrary to how we traditionally learn it in elementary school, it's actually a little bit simpler to show division first. Okay. So say we have two lengths. Okay. We'll say this length is going to be A. And when we have any sort of length, we can move it around, right? We can take, this length here and then simply put it right there. So what we want to do is take our second length, call it B, and actually put it perpendicular here. And in order to do that, we're going to need the perpendicular bisector from before. So what I'm going to do is I'm actually going to extend this line just a bit, marking where A ended. And then I'm going to follow the steps from before to construct a perpendicular line to that point. So now that I have this, what I can do is I can draw a line segment right here, just like that, and then copy whatever our length B is we need. Say B ends up being this long, right? So we have this length here is B. Now what we want to do is we want to actually come up here and grab our unit length, what we're calling 1, and then on A, mark down the point of 1 unit. Call it here. And now we connect these two. Noting that this is going to be a right triangle here. Right? And now this is where we can actually do our division. If we, following the same steps we did here, draw a perpendicular line through our point at 1 unit, notice what we get. These two triangles are similar. And this length here is A, whereas this length here is 1. Which means this length here that we just created, this is going to be B over A. So now using just our ruler and compass, we've constructed the number, or the length rather, B over A. And further than that, actually, this process can be reversed, right? If you wanted to multiply two numbers, we could draw A, right? Go out 1 unit, and then perpendicularly draw our secondary length. And then extend this length, draw the perpendicular, and then now this side is our multiplied value. So, using this process, we can fill in all of the rational numbers here.
All right, well, hello everyone. It's me, Jackie, again, your favorite. Instead of using a chalkboard, this time we're going to use a cool app called GeoGebra. And so this just allows us to do the constructions a little bit faster. Like right here, we have this, instead of a straight edge, it's just a line, and we have our points 0 and 1 on it. And what I'm going to show you how to do today is first I'm going to show you how to find the square root of 2. So I'm showing you that some kind of irrational numbers can also be constructed, and then I'm going to show you how to bisect an angle. So to show how to construct the square root of 2, we have 0 and 1.
what we're going to do is we're going to draw a line perpendicular through our point 1, and then we're going to take the radius of 0 and 1, and we're going to center that circle at the point 1. And then you notice that our perpendicular line and our circle intersect, so we can draw a segment from 0 to that intersection right there. And then using just the Pythagorean theorem, because the length of this side is 1, and the length of this side is 1, then the length of our hypotenuse is square root of 2. And so then if you want to be really explicit, we can take the length of this as the radius of our new circle centered at 0, meaning that this length right here from 0 to our point D here at the end of the circle, this is going to be length square root of 2. Okay, and we're back again. This time we have an angle ABC, and I'm going to show you guys how to bisect this angle. So the first thing that we're going to do is we're going to create a circle centered at B that has a radius of length BA, or length AB, and then we're going to create a point D at this intersection over here with our circle and BC. We're then going to create another circle centered at A, also with radius AB. And we're going to create another circle centered at D with radius AB. And notice that these two circles intersect. And so we're going to create a point E at that intersection. And then a line through BE is actually the bisector of this angle. Well, that's it for all of our constructions. Now we're going to throw it on over to Charlie, who's going to talk to you guys about the formal definition of constructions.
Now that we have seen some constructions, let's talk about the formal definition of a constructible point. So if we keep in mind the three pictures that we saw earlier before, the intersection of two lines, the intersection of a line and a circle, and an intersection of two circles, the formal definition basically lines up exactly here with 1, 2, and 3. However, to define this rigorously, we need to talk about how to actually construct these line segments. So first, a point is constructible if there exists some type of finite sequence of points constructed before, and they must follow this property. If we let S sub j be some subset of this sequence, then the last point in this sequence has to just follow exactly what we talked about earlier. Intersection of two lines, intersection of a line and circle, or intersection of two circles. The first one is that intersection of two distinct straight lines, right? And this last part is what makes it rigorous. It says that it needs to join 2 points of S sub j minus 1. So what this is saying is, if we have some subset S sub j, those two line segments must have endpoints that come from the smaller subset that does not include that last point that was constructed. The same thing is also discussed in bullet point 2 here. In order to create the line segment, those endpoints of that line segment must also come from the smaller subset, not including that last point, P sub j. For the circle, here's a similar story, right? The center must be a point of that smaller subset that does not include P sub j. And the radius also has to be the distance between 2 points of that smaller subset. And lastly, if we have two different circles, their center and the radius of the point between, the center and the edge of a circle, those points also must come from the smaller subset that does not include P sub j. So that's the formal definition. It was made rigorous because instead of just saying, hey, we have two line segments that intersect, we now define a subset where the last point is the constructible point, and the way it's constructed is the endpoints of a line segment or the center and the edge of a circle must come from, like those points must come from a smaller subset, not including that last point. So with that, we'll see, we're going to see proof of a theorem on how, like, why some points are not constructible.